Yesterday we took a look at waves, the properties of waves, and wave motion. I want to spend a little bit of time talking about the wave motion again. When a wave travels in one medium, and by medium I mean the material that it's traveling in, the medium that it's traveling in. Sound right now, as you hear it, is traveling through air. Air is the medium. Sound can also travel through water. In fact, it travels way faster through water than it does through air. The medium in that case would be water. As long as the wave goes in one medium and doesn't change media, as long as it doesn't go from one to the other, then the speed of the wave will remain constant. So therefore, we can describe the motion of the wave using our group A equation. The first one we learned this year, V is equal to delta D over delta T, our constant velocity equation. Now, if we're going from, say, air to water and the speed changes, all bets are off, right? But as long as we stay within the air or stay within the water or whatever the case may be, then we can do this. Now, we also learned another equation yesterday that describes the velocity or the speed of a wave in whatever medium. And it comes from this one, really. It's just a tailored form of the first equation. It says V is equal to F times lambda. We sometimes call this the universal wave equation. It's used for whatever wave, whether it's a water wave or a sound wave or an electromagnetic wave that we're going to learn about next year in Physics 30. V is equal to F times lambda, the frequency times the wavelength. One thing that I want to point out to you before we move on here, frequency of a wave is kind of unique. The speed of a wave when we go from one medium to another can change, although when we stay within one medium it stays the same. But when we go from one medium to another, from air to water, the speed changes. Even if we go from hot or warm water to cold water, the speed of the wave will change. Or from warm air to cool air, the speed of the wave will change. The wavelength of a wave will change when we go from one medium to another. But the frequency of a wave, once the wave has been produced, the frequency will never change. Speed and wavelength stay the same as long as you don't switch materials. Frequency stays the same no matter what. Once a wave has been made, the frequency never changes. Now, that doesn't mean that you can't make a new wave with a new frequency, but once a particular wave has been made, the frequency doesn't change. All right. We use these two equations oftentimes together. Oftentimes we end up using both of them in the same problem. And every once in a while, in conjunction with the third equation that we learned first day of this unit, T is equal to 1 over F. The period is equal to the 1 over the frequency, or some rearranged form of that equation. We had 3 questions for homework last night on page 409. All right, number 2 and 3 it is. 2 says a submarine sonar system sends a burst of sound with a frequency of 325 hertz. The sound wave bounces off an underwater rock face and returns to the submarine in 8.5 seconds. The wavelength of the sound is 4.71 meters. How far away is the rock face? So let's try to visualize this. In fact, let's draw a picture to visualize this. Here's my submarine. It's an oddly shaped submarine, but submarine nonetheless. Here's my rock face. The submarine sends a sound wave toward the underwater rock face. So it produces a sound wave right here, sends a sound wave this way, it bounces off the rock face and returns to the submarine 8.5 seconds later. We're going to say the time here is 8.50 seconds, not the period. This is not the time for one wave cycle. This is the time that it takes a wave to travel a certain distance. It's t, just like it's the value of t when we're talking about driving to Red Deer. Okay? T is an hour and 3/4 or whatever the case may be. It's just any time. In this case, it's the time that it takes the sound to go there and back again. We got a frequency of 325 hertz here, and we know that once a wave has been made, the frequency never changes. The wavelength is 4.71 meters. And we're looking for how far away is the rock face. In other words, we're looking for the distance. Right, the distance that the sound travels. All right, we have basically 2 equations that are applicable here. V equals delta D over delta T, and V is equal to F times lambda. I think I'm going to start with this one because I'm looking for D. It's V times T, but I don't know what V is, so I got to find that. V is equal to F times lambda, which is 325 times 4.71. Who's got a value for speed there? 1530.75, thank you. It's pretty fast, eh? The speed of sound in air is depending upon the temperature of the air. Today, sound would travel a little bit slower than it would have traveled yesterday. The warmer the air is, the faster it travels. But it's somewhere, depending upon the temperature, around 340, 345 meters per second. Here we're talking about 4 or 5 times the value of the speed of sound in air. It travels a lot faster in water than it does in air. All right, let's plug this in here now. 1530.75 times a time of 8.50 seconds. So I think we end up getting something like 1,300 meters. 1.30 times 10 to the 4 meters, which is 1,300 meters, 13 kilometers. Problem is, if we look at our answers, that's not our answer. Our answer is 6.51 kilometers. 6.51 times 10 to the 3 meters. Where did I make my mistake? What have I done wrong, Matt? Why should I have divided the time in half? I mean, it tells me it takes 8.5 seconds. Why should I make that 4.25? Okay, good. It's important to note here that we do have to divide the time in half, but there's got to be a reason to do that. We don't just, say, oh, I can see the answer is half of what it is, so I got to divide the time in half. Why are we dividing the time in half? We're looking for this distance, the distance between the submarine and the rock face. We have a time that it takes the sound to go there and back again. So we have double the time that we want. We have to either divide that time in 2 and multiply 1530.75 times 4.25, get 6.51 kilometers, or we could take this distance and divide it by 2. So solve for the distance there by using half the time, or solve for the distance there and back, and then divide the distance by 2. Something has to be divided by 2. Okay. And number 3 says a fisherman anchors his dinghy in a lake 250 meters from shore. The dinghy rises and falls 8 times per minute. He finds that it takes a wave 3 minutes to reach the shore. How far apart are the wave crests? Don't blindly just look at this and say, 3 minutes, that must be the period, or 250 meters, that must be the wavelength. 250 meters from shore, that's not the wavelength. If that's the wavelength, we got a big wave, right? If the wavelength was the same as the distance from the dinghy to the shore, that would be quite a coincidence, especially when it's such a big number. That's not wavelength in this case. That's just going to be delta D. We've got a time that it takes the wave to travel to the shore of 3 minutes. It's not the period. The time for one cycle of the wave is not the time that it takes the wave to go to the shore. If it was, that would be quite a coincidence again. It's not likely going to be 3 meters. This is 8 times per minute thing. The dinghy rises and falls 8 times per minute. Yeah, Toby? Is your hand up? That's the frequency. Although we want to make sure that we convert that to hertz, right? Not times per minute, but times per second. We want to find out how far apart the wave crests are from one another. In other words, the wavelength. This is 180 seconds. 8 times per minute is 0.1333 hertz. Thank you, Kobe. We're going to solve for lambda here. Let's say V is equal to F times lambda, because it's the only one we have with lambda in it. V over F, but we don't know what V is, so let's find it. It's distance over time. 250 meters divided by 180 seconds. 1.3888. Okay. So now we take that, plug it in here. Divided by the frequency of 0.133. And a lightning fast calculation this time. Do the math there, and we end up getting 10 meters. Rounded to 2 digits, 10 meters. All right, I'm going to give you a few minutes here, not a great deal of time, but a few minutes to work on some questions on page 410. Questions number 1 to 10, please. What you don't finish in the next few minutes is going to be homework tonight.